Hello, welcome back. In this video, we discuss about the concept moment of a force. In the previous video, we discussed about particle approximation, where size or volume of an object is neglected. In this case, the forces are assumed to be acting through its center of mass. If the net force acting is zero, then the object is said to be in static equilibrium. Now consider the object is acted by a net resultant force Fr. According to Newton's second law, this resultant force causes acceleration to the object. The equation that governs this motion is F equals ma. In this case, F is the net resultant force Fr. Due to acceleration, the object will be in motion and its velocity vector will change with respect to time. The particle approximation is valid if the resultant force is acting through the center of mass of a real object with a definite size. In this case, the force results in acceleration and it will move, or we call it as translation motion. Now imagine that the resultant force is not acting through the center of mass. In such a case, this will not only translate the object but also try to rotate it. The rotational effect of a force vector is quantified by another vector quantity called moment of a force. To define moment vector, we need a force vector, a point of application, and a reference location about which moment is calculated. Let R vector is the position vector of the location A with respect to point O, and F vector is the force acting on the object where A is the point of application. O is the reference point at which moment is calculated. Now, the moment vector F is defined as R cross F, where R is the position vector of point of application A from reference point O, and F is the force vector. Now consider a simple problem. If beam fixed at one end is acted by a force of 100 Newton in magnitude, calculate the moment of this force about the point O, which is the fixed end. So by definition, the moment vector is R cross F. Now we can see that R is the position vector of the point of application A from O is 2 meters in the J direction. So we can write the vector as this. Similarly, the force vector, which is 100 Newton acting in the minus K direction, we can write as 0I plus 0J minus 100K. The moment vector is R cross F. We will substitute R and F here. Then the R cross F is calculated as the expansion of the determinant formed by the two vectors R and F. So it starts with the first row ij k, and the second row is the vector R, coefficient of R, and the third row is the coefficient of vector F. So the determinant expansion is straightforward. You start with I, then you have a square bracket, then you multiply these two elements minus these two elements, then you close the bracket, then put a minus sign, then you start with the J, then you forget about this row and this column and multiply these two elements minus these two elements and put a close the square bracket, then plus sign and K, and this row and this column will not be considered, and you multiply these two elements minus these two elements. So that's how you get the moment vector as 200 I Newton meters. We will represent the R vector as 2J in this direction, and F vector is acting downward. So the M vector is acting in the minus I direction, so this way. So this is a clockwise moment, okay, clockwise moment. Uh, Another problem, the only difference here is the force is acting in the k direction, positive k direction. So we have the same position vector r, and the force vector is in the positive k direction, which is 100 meters. So the same process for the calculating the moment vector r cross f and the determinant. Then you get this as 200 I Newton meter. And physically, this is represented as forces acting upward, and position vector is in this the acting in the I direction, j direction. And the moment vector is in the I direction. So this is a anti-clockwise moment. In this case, we can define this as an anti-clockwise moment. Finally, another problem, we have a structure uh, uh, which is acted by multiple forces F1, F2, and F3, and different dimensions are given so that we can find out the position vectors of A and point B where the forces are acting. And the reference location is O, so you need to find out the net resultant moment and its direction cosines on this configuration. So we will solve this problem in class. Here is some hint. All you have to do is find the moment of each forces uh, with respect to O. We have three forces, so you have to find three moments of each forces about reference O. Then you add all of them together. Once you have the net resultant moment vector, you can calculate the direction cosines using the methods we discussed in the previous videos.